I'm very glad to be here to give a talk today. Today, I'd like to talk about the chiral magnets studied by small angle neutron scattering and muon spin rotation. So, so this is one of my memorial pictures. So Inoue Sensei told us that history of our collaboration. So this picture took in 2004. This is the first experiment with Inoue Sensei trial in Vancouver. So during the experiment, we went to sea to catch the big salmon. And after that, we ate this the dormitory of the trial. So this is my good memories at the beginning of the collaboration with Inoue Sensei. Anyway, okay, so this is my outline of my talk. So first, I'd like to introduce the J-PARC. Then today I'd like to talk two topics. The first one is new magnetic intermediate state found in the mangan state side. And next one is a pressure effect on uniaxial chiral magnet, chromium, niobium, sulfur. So finally, let me summarize my talk. Okay, as a beginning, I'd like to introduce J-PARC, which is a Japan Proton Accelerator Research Complex. Do you know where is J-PARC? Of course, it's in Japan, but it's in the Kanto area in Japan, and it's located in the Tokai village in Ibaraki Prefecture. Here, it is about 100 kilometers from Tokyo. So the campus is about the 1 kilometers north and south direction, and 500 meters for the east and west side. So it's a large areas. And in J-PARC, we have 3 experimental facilities. One is a hadron experimental facility, and the second is a neutrino experimental facility. And the last one is a materials and life science experimental facility, so-called MLF, in which we have many instruments for the neutron and muon experiments. This is top view of MLF building. So the accelerated proton beam comes from left-hand side to the right-hand side. And there is 2 targets. First one is a muon target, and the second one is a neutron target. The 5% of proton beam provide a muon beam, and the rest of proton beam make a neutrons. So there are 23 neutron beam lines in MLF. And here is it's written in Japanese, but so this is a small angle neutron scattering instrument, which I'm in charge of now. Okay, before I show you our results, I'd like to introduce the brief introduction of neutron scattering and muon spin rotation technique. First, the neutron scattering technique. So when you probe the matter, we usually use X-ray or electron or neutrons for diffraction measurement. For X-ray case, it's scattered by the electromagnetic interaction. And for the electron case, it's scattered by the electrostatic interaction. And then the neutrons case, there are 2 interactions. One is a nuclear interaction, and second one is a magnetic scattering by the dipole-dipole interaction. So the neutron can detect the crystal, not only crystal structures, but also magnetic structures. And neutrons have wavelengths similar to the interatomic distance, and it can therefore differ. So, for example, there are a wide range of wavelengths from 0.05 to 20 angstroms, or it can it is observed so the different scales using these wavelength neutrons, and also same energy range that the atomic and the electronic processes. So, for example, the ED to ED with the possibility to detect changes less than micro ED. For example, the tunneling process or rotation or vibration of molecules and electronic transitions and diffusion. For example, the ion diffusions in particle materials. So neutron can use for the static structures measurement and also dynamic measurement. And one more feature, interaction electron matter is via nucleus and not with an electron cloud. So compared with X-ray, then the scattering length for atom does not depend on atomic number C. For example, in case of X-ray's case, the scattering cross section is proportional to the atomic number, but for neutron's case, it doesn't. So we can detect the hydrogen and also the isotope deuterium, or we can compare with the so in this case, it's easy to write atoms. For example, the hydrogen, lithium in presence of heavy atom. And also, it's easy to distinguish next neighbor's atoms in the periodic table. For example, the iron, cobalt, nickel. In case of X-rays, it's not easy to distinguish this sample, but for the neutron, it's very easy. And using these features, my instrument can detect the for the crystal structures or large scale of structure from the submicron to angstrom regions. So the name is small and wide angle neutron scattering instrument, HICAM. HICAM means wide view. The HICAM can measure wide Q range. So because it's important to understand the functions by studying hierarchical structures. For example, this structure, the length scale of this structure is from wide length scale. So from the submicron to the, what to say, for example, the angstrom. So these one very wide range. So HICAM is designed to measure such kind of scale at once, one measurement. Because how does HICAM do? We use the white neutron beam. It means the wavelength of neutron is from the 0.8 angstrom to the 8 angstrom. So this kind of white beam comes from the target to the sample, then it's scattered. Then after that, we measure the scattered neutron using wide angle band detectors. So it means that wide two-theta. The combination of the white beam and these many detector banks can provide wide Q measurement. Okay, so then I'd like to talk about the brief introduction of USR measurement, muon spin realization. So the USR measurement is not diffraction, like X-ray or neutron or electron case. So the muon, positive muon has spin, and its spin is 100% spin polarized. And when we inject the muons into the sample, then the muon stops in the sample. After that, it senses an internal field and process muon spin process in the sample. Then after the average lifetime, muon decays into positron and 2 neutrons. And in this case, the positron tends to be emitted along the muon spin direction. So counting these positrons using the backward and forward counters, we can extract the time evolution of the spin polarization, muon spin polarization. So positron intensity as a function of time after implantation is expressed like this for the forward counter and backward counters. And taking the ratio of these two parameters like this, then it shows the time evolution of muon spin polarization. For example, there is no magnetic no magnetism in the sample. Then we apply the magnetic field perpendicular to the muon spin, initial muon spin polarization like this. Then the muon stops in the sample. The muon spin presses around the internal field. Then we observe the number of positrons at backward and forward counter. This is show the time evolution of the number of positrons obtained by backward counter and forward counter. As you can see, so there is a high shift. So then we take this ratio, we can extract the time evolution of muon spin polarization, like cosine curvature. It's like a precession of the muon spin. And when we use a transverse field universal measurement technique between transverse field and magnetic field applied perpendicular to the initial muon spin like this, then this signal provides an internal field distribution because muon stop in the sample at several points on interface. So it means that random sampling the internal field, muon can pick up the random sampling effect, pick up the internal field randomly. After that, we can extract the internal field profile in the real space using the magnetic model. For example, this is the case for the flux line lattice superconductors. Flux line lattice makes inhomogeneous magnetic field distribution. When we inject the muon into this sample, then muon flow the several internal fields. So the internal field is changing. For example, the top of flux in the internal field it takes maximum, but the bottom of this saddle point, then the internal field is very low. So muon can detect every internal field at every basis. Then we can obtain this time evolution of the muon spin polarization spectra. And when we Fourier transform this spectra, then we can obtain the internal field distribution. So this is a frequency which corresponds to the internal magnetic field. So we can obtain these such kind of specific internal field for the superconducting flux line lattice in the superconductor. So the neutron can take the long range for the case for for example, the crystal structure or magnetic structure or something like that. But for the muon's case, it doesn't matter whether it has long range order or not. Just measure the internal field information. Okay, then I'd like to talk about the first topic about new magnetic intermediate space, so-called weak phase in mangan system. So here is my collaborators. This is an international collaboration with a Spanish group and Canadian group and the Japanese group. And the key person is Dr. Miguel. This is a part of his PhD thesis thing. He took his PhD in this July. So, and first I'd like to introduce about the chiral magnet in P20 type materials, which is composed of the transition metal and carbon mix, 1-to-1 ratio. Such a material has a cubic crystal structure, and space group is P213, which is a chiral structure. So when we see this crystal along the 1-1-1 direction, there is a two crystal structures. So when we focus on this gray atom, left-hand side, it stacks along this 1-1-1 direction, like a clockwise. On the other hand, this side, this gray atom stacks on the 1-1-1 direction, counterclockwise. So this is a chiral structure, so left-handedness or right-handedness, as you know. And in these chiral structures, the magnetic structure is also affected by this chirality, like this. So there, in this case, asymmetric interaction, so-called the Dzyaloshinskii-Moriya interaction, appears, and it competes with the exchange interaction. For example, when the exchange interaction takes a ferromagnetic interaction, then non-chiral material makes a ferromagnetic state below the transition temperature. But in the chiral magnetic case, because of the Dzyaloshinskii-Moriya interaction, which twists the next neighbor's spin, then the magnetic structure takes like a spiral structure. And its period is about 5 to 200 nanometers, which is incommensurate with the lattice parameter. And also, nowadays, so in this case, the propagation vector is just one direction. But when it takes 1/2000 structure like this, then the skyrmion lattice appears, which is the spin. This is a, how to say, kind of particle. So particle form the structures, magnetic particle form structures. Okay, then here show the magnetic field versus a temperature phase diagram of mangan silicide. As you can see, below transition temperature, it becomes a helical structure. It's kind of a spiral magnetic structure. And when we apply magnetic field, then this spiral changes to the conical structure, because the magnetic moment tends to align the applied magnetic field direction. And when we apply field more and more, then finally this magnetic moment aligns along applied magnetic field. Then the system becomes a forced ferromagnetic state. And one of the features of the mangan silicide phase diagram is A phase, which was found in 1980s, but there at that time nobody understands what it is. But in 2009, according to the small angle Newton scattering measurement, they found a 6 called black spot, and they suggest the existence of skyrmion lattice in A phase. After that, this is a K-space measurement, and after that, the Lorentz measurement, which is in real space measurement, but they observe also this kind of lattice structure in skyrmion. So nowadays, it is considered that the skyrmion lattice is in the A phase, but it appears just below TC and very narrow magnetic field range. On the other hand, the theoretical approach is theoretically, in 2017, a new state was suggested at low temperature and high magnetic field region. So this is a phase diagram, magnetic field and temperature. And here is, they suggest the unknown state at low temperature region. And also, they suggest the skyrmion, metastable skyrmion lattice even at low temperature. After that, one measurement in manganese silicide, they said that there is a metastable skyrmion lattice even at low temperature. And also other materials. So this is also a cubic chiral material, kappa 20703. They even in this material, the tilted conical state and also the low temperature skyrmion lattice was observed. So there is something at the low temperature region, but in manganese silicide, at this moment, we don't observe anything except the metastable skyrmion lattice. So what is unknown state? Is it real or? Then we try to find this unknown state. First, our group have performed a specific heat measurement and also DC magnetization measurement. But there is no evidence of unknown states, just we found the anomaly around transition temperature. However, finally, we succeeded in finding the anomaly at low temperature near critical field by the AC magnetization measure. So this is the result of magnetic field dependence of the AC magnetization. And when we focus on this region, it's very tiny, but we have found anomaly like this. And when we check this carefully, we can find this new phase. We call this B phase compared to this A phase. So there is at low temperature region and high magnetic field, which is suggested by the theoretical calculation. Then, what is the microscopic nature of this phase? So to understand this nature of B phase, we have performed a small random neutron scattering and MnSi measurement. And small random sound measurement was performed at ILL and J-PARC with these conditions. And also the MnSi measurement was performed at my memorial place of triangle. These conditions. Okay, then I try to show you the results, sound results first. Experimental condition is applied field is always parallel to 1-1-1 direction. And the sound measurement observes the diffraction which transmitted the sample like this. And here is a result obtained at 2 Kelvin and 28 Kelvin. And there are two conditions. The first condition is like this. So a magnetic field is perpendicular to the neutron incidentally. In this condition, we can observe the conical phase, the black spot due to the conical phase. And here is this condition here and here. As you can see, there are many black spots at zero applied field because the magnesium side has a cubic crystal structure. So the chiral axis, the equivalent chiral axis, there are 4 equivalent chiral axes. So the conical phase from the one chiral axis and also the other chiral axis are observed. And these two small peaks was a multiple scattering. And when we apply
sorry. It is the one direction.
One direction.
Then there are 3 equivalent colors, right? Why for one direction is for 3. Parallel to the one parallel axis. Why you have 4 sets?
Sorry, so this is one and 3, 2. And these 4 spots are multiple scattering. It's not.
Yeah. Maybe 3. Why?
Okay. So this is because these 2 chiral axes satisfies the scattering condition. So there are another 2 peaks, but it's not on the plane. Scattering plane. So then, when we apply magnetic field along the 111 direction, then the chiral axis merge into the 111, just 111 direction. So these peaks merge to this horizontal black spot, and then after that we observe that just one chiral axis like this. And from this result, we can say that even in the B phase region, we don't have any anomaly, but just observing black spot due to conical phase. And for the 28 Kelvin, it's also observed but when we apply field, it merges into one chiral axis, and it shows a similar case. So there is no difference between the 2 Kelvin and 28 Kelvin. And second experimental condition is magnetic field applied parallel to the neutron field. It corresponds to the upper panel of each temperature. And for this condition to observe skyrmion lattice. So in A phase, 28 Kelvin is A phase. We have observed the skyrmion lattice. So it's very low intensity, but we have 6 black spots here. On the other hand, at 2 Kelvin, even in the B phase region, we don't have any black spots. So from this measurement, we can conclude that B phase is different from A phase. And also, we can extract the possibility of the shielded conical phase, like kappa 2. Okay, then here shows the magnetic field dependence of integrated black spot intensity and propagation vector at several temperatures. As you can see, the propagation vector is independent of the magnetic field at all temperature regions. But here, the intensity of the black spot behaves funny behaviors. So when we apply the magnetic field, the intensity increases and decreases. But when we decrease the magnetic field, it follows the same intensity about 0.4 Tesla, but below 0.4 Tesla, there is a hysteresis. And this behavior was also observed in different magnetic field direction conditions like this. At this moment, we are not sure what happens in this region, but there is this is some results. And from these SANS results, the origin of B phase is not similar to the low temperature skyrmion lattice or tilted chiral helical magnet, but it's still unclear. Then we do the USR experiment to understand the internal field distribution in each phase. The mangan silicium is very old material, so there are many USR papers in mangan silicium. So we know where muon stop in the mangan silicium. There are 4 muon sites in unit cell. And then we perform the transverse field experiment, which in the applied field is perpendicular to the initial speed direction. This is the typical USR data obtained at 2 Kelvin. So there is many frequency signals. And when we Fourier transform this time spectra, then we can obtain the internal magnetic field distribution. And this peak is coming from this H1 site muons. This muon is internal field. And the other muons, 3 muons, which is on the same plane, on the 111 plane. And these 3 muons is broad internal field distribution. And then we perform the MnSi measurement at various points like this. And we found the internal field distribution. For example, here show the internal field distribution against several magnetic field at 2 Kelvin. So in this case, we measure the helical phase, conical phase, D phase, and post-fermat phase. And also the field distribution looks different, like helical, conical, D phase, and post-fermat phase. But I can say is the magnetic field distribution, this asterisk stands for the applied magnetic field. So for this, so the yes, applied magnetic field. And from this measurement, we can say that this peak from the H1 muon side is not change, but for the distribution from H2 side differ from the applied magnetic field. It means differ from each phase. And then here show the field, magnetic field dependent, temperature dependence of magnetic field at 0.55 Tesla. In this case, the B phase, conical phase, post-ferromagnetic phase, and normal phase. So we observe the difference between each phase, but even in the B phase and the conical phase, the difference looks very small. It looks similar like this. So H1, the internal magnetic field distribution from H1 muon keeps like this, and also the field distribution from H2 side has like these 2 peaks structures. And also, here show the field distribution of data around A phase. And around in the A phase, the internal field distribution is completely different from conical phase, like this, which is due to the skyrmion lattice. And also, this is temperature dependence of the distribution. Skyrmion lattice is special distribution. Then, to extract what kind of magnetic structure exists in the conical E phase and the skyrmion lattice phase, we need a model to extract such kind of internal field, extract the magnetic structure. Then, according to the reducible representations, we have several conditions. So the data propagation vectors and the space group, and we know the Mangan position at OA micro position. So using this condition, we can estimate the magnetic structure of Mangan C site, like these three magnetic structures, which is like this. So, Mangan 1, Mangan 2, 3, 4. So each Mangan has a spin. And in case of M lambda 1, Mangan 1 spin is along to the 1, 1, 1 direction, and the other spin along in the 1, 1, 1 plane. Or in this case, all spins are in 1, 1, 1 plane, but spin directions like this. And in lambda 3 case, all spins are on the 1, 1, 1 plane, but the angle of M Mangan 1 and the other takes phase shift. And according to the previous experimental results and theoretical analysis, this magnetic structure is most consistent. And in which the magnetic moment contained in planes 1, 1, 1 direction is a small phase shift between both orbits, from one and the others, 2 degrees or several degrees. But even in this condition, using this condition, phi is not fixed. So this value is a prediction value. So nobody, we cannot decide only this condition. So using the magnetic structure model of M lambda 3, we fit the USR data for both time spectrum and Fourier transform Fourier spectrum. As you can see, we have a good fitting result using this magnetic structure model. And this shows the magnetic structure model. And this MH and MU is a component of the magnetic moment along the 1, 1, 1 direction and perpendicular to the 1, 1, 1 direction. So when we apply the magnetic field, when we increase the applied field, the MU component of MU increases with so we use this model, then we fit the data like the previous slide. And this and the one condition is phi for Mangan 1 is pre-parameter, and the other Mangan's phi fixed to 0. It means that there is a pi degree shift between Mangan 1 and the other Mangan, and it has a rotation. It has a chiral structure. Then we can fit, we use the only three parameters to fit the VSR data: initial phase, rotation, relaxation rate, and angle between the orbits. So these 5 parameters. So initial phase decreasing with increased magnetic field. It's very common to transfer speed measurement. And for the relaxation rate, it gradually increases with increasing magnetic field, but it jumps at the 0.7 Tesla because at this magnetic field, the system becomes a post-permanent state, so the relaxation rate increases. What we should focus on is these results. So this is the pi, the angle shift between the manga 1 and the other manga side. So it keeps constant 0.3 Tesla, but it changes, the tendency changes above like this field region. And this field is similar to the anomaly in the AC magnetization. So these magnetic field correlated with this behavior. So the origin of B phase is a slight reorientation for such kind of conical cases in the unit cell. Then, as I show you, there is no anomaly in the specific heat measurement, and also the propagation vector. But it is inconsistent with no change in propagation vector, but in average moment, just modulus. And also it is consistent with null effect in heat capacity because there is no change entropy. Then let's move back to the results of Sun's experiment. So we have a so then we explain the magnetic field dependence on intensity obtained by Suns. So the Sun's intensity is expressed like this, and N and Mu is obtained by magnetization measurement, and pi is obtained by the fitting analysis of the BSR data. So then we calculate the intensity of each temperature data. Then, as you can see, so the calculation data shows good agreement with the results. However, when we fix the phi equal to 0, then here is the results. So there is there is a little difference between the finite pi and 0 pi like this. As the Sun's technique exhibits limited sensitivity in resolving the variation internal of P structure at atomic scale. So these results says so both Sun, Neutron, and the Muon experiment is very important to understand totally what happened in the phase system. So this is my conclusion of one first topics. And we have observed the anomaly in phase from the AC magnetization, and we found, and this is already published. And we conclude that this is the origin of B phase compatible with the relative orientation of phase. So this is the second topic of the pressure effect of uniaxial chiral magnet. So maybe you know these materials. It's very famous for the chiral magnet. It shows the chiral soliton lattice, and the transition temperature is about 135 Kelvin, and it has in magnet chirality. It is observed during the 1983. And Ito sensei studied the pressure effect of these materials using a powder sample. And both using powder sample of AC magnetization from the AC state magnetization measurement. And the lattice parameter and transition temperature increases with increasing magnetic applied pressures. Then we would like to know what's happened with Dzyaloshinskii-Moriya interaction and period chiral helical magnet. So we have performed some experiment under pressure helical J-PARC using a single crystal. So this is the first experiment at helical under high pressure. So we prepare, the Kosaga-san prepared for their 17 single crystals. These crystals are all aligned like this direction, and they are glued on the aluminum sample cell. And this sample cell is in the piston feeder type pressure cell like this, and which is adapted to refrigerators. Then we measure the pressure effect at temperature range between the 3 to 150 K, and we applied pressure 0.6 and 1.2 gigapascal. These kind of pressures. And here the results are we successfully observed the two graphs from the conical base and each pressure. And from these results, we can extract the temperature dependence of intensity and propagation vectors. And from these results, we found that the transition temperature increase with increasing pressure is consistent with the other sample state. And also, we found that the propagation vector increases with increasing applied pressure. Then from these results, we can extract the period of the chiral magnetic state, and also we extract the transition temperature and the ratio of Dzyaloshinskii-Moriya interaction and the exchange interaction. From these results, the helimagnetic period error becomes smaller with an increasing pressure, but this ratio is not similar to the shrinkage of C-axis. So C-axis is a chiral axis. When C-axis shrinks, then period shrinks, but the relation is different. And Dzyaloshinskii-Moriya D over J becomes larger compared with the decrease of transition temperature. This is correspond to the exchange interaction. But from these results, we can say that DM interaction is increased by pressure. But in this case, so we cannot understand which the pressure affect not only DM interaction, but also the exchange interaction. So we are not sure which is the dominant. So this is summary, but we are trying to do the uniaxial stress measure to extract the effect of pressure effect to the DM interaction. And we already did an experiment, and now data analysis is performed by the Kosaga-san. Okay, so this is a summary of the second topic, and this is a final conclusion. So today I introduced what is J-PARC, and the J-PARC FLF provides a neutron and a muon beam, so it is very powerful tool to study the magnetic structures and also the magnetic phase. And I showed that these two topics. Now, finally, neutron and the muon techniques are powerful tools for studying the magnetic properties. So if you are interested, please ask me. Thank you for your attention.